What if everything you thought you knew about reality was just the tip of the iceberg? What if the universe we see, touch, and experience is only a fraction of what truly exists? Imagine a world where hidden dimensions, invisible to our eyes, hold the keys to understanding the deepest mysteries of existence. From the tiniest particles to the vastness of space, these unseen realms could rewrite everything we know about the cosmos. Today, we're diving into 30 mind-blowing theories about the universe's hidden dimensions of existence. Theories that challenge our perception of reality, explore the fabric of space and time, and even suggest that our universe might be just one layer of a much grander, multidimensional tapestry. Are you ready to uncover the secrets that could change how you see everything? Stay with us, because by the end of this journey, you'll discover how these hidden dimensions might hold the answers to questions we've been asking for centuries. Let's begin. Now, let's step into the first theory that opens the door to these hidden dimensions: string theory. At its core, string theory proposes a radical shift in how we understand the building blocks of the universe. Instead of particles being tiny, point-like objects as traditional physics suggests, string theory imagines them as incredibly small, one-dimensional strings. These strings vibrate at different frequencies, much like the strings of a guitar, and it's these vibrations that determine the properties of particles, whether they're electrons, quarks, or even the particles that make up light. But here's where it gets truly fascinating. These strings don't just vibrate in the 3 dimensions we're familiar with. They exist in higher dimensions we can't see, but that could be woven into the very fabric of reality. What does this mean for our understanding of the universe? Well, string theory suggests that these hidden dimensions might be the key to unifying the fundamental forces of nature: gravity, electromagnetism, and the nuclear forces. It's a framework that could potentially solve one of the biggest puzzles in physics: how to reconcile the laws of quantum mechanics, which govern the very small, with general relativity, which describes the behavior of the very large. By introducing these extra dimensions, string theory offers a way to bridge the gap, suggesting that what we perceive as separate forces might actually be different manifestations of the same underlying phenomenon. But why can't we see these extra dimensions? According to string theory, they might be curled up or compactified, so tiny that they're beyond our current ability to detect. Think of it like a garden hose. From a distance, it looks like a one-dimensional line, but up close, you can see it has a circular dimension wrapped around it. Similarly, these hidden dimensions could be all around us, just too small for us to notice. The implications of string theory are profound. If proven true, it wouldn't just explain the nature of particles and forces. It could also provide a deeper understanding of the universe's hidden dimensions, offering clues about the origins of space, time, and even the Big Bang itself. It's a theory that challenges us to rethink not just what we see, but what we can't see, opening up a universe of possibilities that stretches far beyond our current understanding. And with that, we've only just begun to scratch the surface. Next, we'll explore how string theory evolves into something even more expansive: M-theory, which takes these ideas to a whole new level. Building on the foundation of string theory, we now venture into the realm of M-theory, a bold and expansive framework that takes the concept of hidden dimensions to an entirely new level. While string theory introduced us to the idea of vibrating strings existing in higher dimensions, M-theory goes even further, proposing that the universe isn't just made up of strings. It's composed of something even more complex: membranes, or branes for short. These branes can exist in up to 11 dimensions, weaving a tapestry of reality that's far richer and more intricate than we ever imagined. So, what exactly is M-theory? Think of it as the next evolution of string theory. In the late 1990s, physicists discovered that the 5 different versions of string theory weren't actually competing ideas, they were different facets of a single, overarching theory. M-theory emerged as the unifying framework that tied them all together, suggesting that each version of string theory was simply a different perspective of the same underlying reality. This was a monumental breakthrough as it provided a way to reconcile seemingly conflicting ideas and offered a more complete picture of the universe's fundamental structure. One of the most striking aspects of M-theory is its proposal of 11 dimensions. While string theory hinted at the existence of extra dimensions, M-theory solidifies this idea, suggesting that these dimensions aren't just mathematical curiosities, they're essential to understanding how the universe works. Imagine our familiar 3 dimensions of space and one of time as just the surface of a much deeper reality. The additional dimensions proposed by M-theory could be compactified, curled up so tightly that they're invisible to us, or they could be vast and expansive, hidden from our perception in ways we're only beginning to explore. But why 11 dimensions? The answer lies in the mathematics. M-theory's equations only work consistently in 11 dimensions, providing a natural framework for unifying the forces of nature. This includes gravity, which has long been the odd one out in the standard model of particle physics. By incorporating gravity into the same framework as the other fundamental forces, M-theory offers a potential solution to one of the greatest challenges in modern physics, the quest for a theory of everything. The implications of M-theory are staggering. If correct, it could explain not only the behavior of particles and forces, but also the very fabric of space and time. It suggests that our universe might be just one brane, floating in a higher dimensional space, with other branes potentially hosting entirely different universes. This idea ties into the concept of the multiverse, where countless universes could exist alongside our own, each with its own unique set of physical laws. As we continue to explore M-theory, one thing becomes clear: it challenges us to think beyond the limits of our perception. It invites us to consider a universe that's far more complex and interconnected than we ever imagined, where hidden dimensions hold the keys to unlocking the deepest mysteries of existence. And with that, we're ready to take the next step in our journey as we delve into the brane world scenario, a theory that builds on these ideas to paint an even more vivid picture of the cosmos. Now, let's take a closer look at the brane world scenario, a fascinating theory that builds on the ideas of M-theory to reshape our understanding of the cosmos. Imagine our universe not as an isolated entity but as a 3-dimensional membrane, or brane, floating within a higher dimensional space. This concept suggests that the fabric of reality might be far more layered and interconnected than we've ever realized. In this scenario, our universe is like a sheet of paper suspended in a vast, multidimensional expanse. But here's the twist: other branes could exist alongside ours, each potentially hosting its own universe with its own unique set of physical laws. These branes might be separated by dimensions we can't perceive, yet they could still influence one another in subtle but profound ways. This idea opens up a whole new way of thinking about the structure of reality, where the boundaries between universes are not as rigid as they seem. One of the most intriguing implications of the brane world scenario is its potential to explain some of the universe's greatest mysteries, such as gravity and dark matter. Gravity, for instance, might appear weaker in our universe because it's not confined to our brain. It could be leaking into the higher dimensional space around us. This leakage could explain why gravity is so much weaker than the other fundamental forces, a question that has puzzled scientists for decades. Dark matter, too, might find an explanation within this framework. Some theories suggest that dark matter could be ordinary matter existing on a nearby brane, invisible to us but exerting a gravitational pull on our universe. This would mean that what we perceive as dark matter might actually be the influence of another brane, hidden from our view but still shaping the cosmos in ways we're only beginning to understand. The brane world scenario also raises profound questions about the nature of space and time. If our universe is just one brane among many, What does that mean for the flow of time or the expansion of space? Could interactions between brains have sparked events like the Big Bang, or even triggered cosmic phenomena we've yet to discover? These are the kinds of questions that make this theory so compelling. It challenges us to rethink everything we thought we knew about the universe. As we explore the brane world scenario, we're reminded that the cosmos is far more complex and mysterious than it appears. It invites us to consider a reality where hidden dimensions and parallel universes are not just science fiction but integral parts of the cosmic puzzle. And with that, we're ready to move forward as we dive into the next theory, Calabi-Yau manifolds, where the hidden geometry of the universe takes center stage. Now, let's shift our focus to a concept that might sound like it belongs in an abstract art gallery, but is actually a cornerstone of modern physics: Calabi-Yau manifolds. These intricate, multi-dimensional shapes are not just mathematical curiosities, they're thought to hold the key to understanding the hidden geometry of the universe. If string theory is the blueprint for reality, then Calabi-Yau manifolds are the architectural details that bring it to life. To visualize these manifolds, imagine a shape so complex that it twists and folds in ways our three-dimensional minds can barely comprehend. Picture a six-dimensional object, yes, 6 dimensions curled up into a tiny, compact form. These shapes are so small that they're invisible to us, yet they're believed to exist at every point in space, shaping the very fabric of reality. In string theory, these manifolds are the stage on which the strings of the universe vibrate, determining the properties of particles and forces we observe. But why are these shapes so important? In string theory, the extra dimensions required to make the math work beyond the 3 spatial dimensions and time we experience are thought to be curled up into these Calabi-Yau manifolds. This compactification is what allows the universe to appear three-dimensional to us, even though it might have many more dimensions hidden from view. It's like looking at a tightly wound ball of yarn from a distance. It seems smooth and simple, but up close, you see the intricate loops and knots that make up its structure. The geometry of these manifolds isn't just a mathematical quirk. It has profound implications for the universe. The specific shape of a Calabi-Yau manifold determines how strings vibrate, which in turn dictates the properties of particles like electrons, quarks, and photons. In other words, the hidden geometry of these shapes could explain why the universe has the laws of physics it does. A different Calabi-Yau shape might lead to a universe with entirely different particles and forces, or perhaps no universe at all. One of the most fascinating aspects of Calabi-Yau manifolds is their connection to symmetry. These shapes are incredibly symmetrical, with patterns that repeat in ways that are both beautiful and mathematically elegant. This symmetry isn't just for show. It's thought to play a crucial role in stabilizing the extra dimensions and ensuring the consistency of the universe. Without this symmetry, the hidden dimensions might unravel, leading to a cosmos that looks nothing like the one we inhabit. As we explore the world of Calabi-Yau manifolds, we're reminded that the universe's hidden dimensions aren't just abstract ideas, they're woven into the very fabric of reality. These shapes challenge us to think beyond the limits of our perception and consider a cosmos that's far more intricate and interconnected than we ever imagined. And with that, we're ready to move forward as we delve into the next theory, the holographic principle, where the universe itself might be a projection of information stored on a two-dimensional surface. Now, let's step into a theory that feels like it's straight out of a science fiction novel but is grounded in cutting-edge physics, the holographic principle. This mind-bending idea suggests that our three-dimensional universe might not be as it seems. It could actually be a projection of information stored on a two-dimensional surface. Imagine the universe as a cosmic hologram where everything we see, touch, and experience is encoded on a flat, two-dimensional boundary. It's a concept that challenges our very understanding of reality and opens up a new way to think about space, time, and the hidden dimensions that might shape our existence. The holographic principle first gained traction in the study of black holes. When scientists tried to reconcile the behavior of black holes with the laws of quantum mechanics, they stumbled upon a startling realization. The information about everything that falls into a black hole isn't lost forever. Instead, it's encoded on the black hole's event horizon, the two-dimensional surface that marks the point of no return. This discovery led to the idea that the universe itself might operate in a similar way, with all the information about our three-dimensional reality stored on a two-dimensional boundary. It's as if the universe is a giant cosmic movie, and the screen it's projected on is a flat, two-dimensional surface. But how does this connect to hidden dimensions? The holographic principle suggests that the extra dimensions we've been exploring, like those in string theory or Calabi-Yau manifolds, might not be separate from our three-dimensional world. Instead, they could be encoded within the two-dimensional surface, acting as a kind of blueprint for the universe. In this view, the hidden dimensions aren't physical spaces we can travel through, but rather mathematical structures that define how the holographic projection works. It's a radical reimagining of what dimensions are and how they shape the cosmos. One of the most intriguing implications of the holographic principle is its potential to solve one of the biggest mysteries in physics, the nature of gravity. In this framework, gravity might not be a fundamental force but rather an emergent phenomenon, arising from the way information is encoded and projected from the two-dimensional surface. This could provide a new way to unify quantum mechanics and general relativity, two theories that have stubbornly resisted reconciliation for decades. It's a tantalizing possibility that could reshape our understanding of the universe's deepest workings. As we explore the holographic principle, we're reminded that the universe is far stranger and more interconnected than we ever imagined. It challenges us to think beyond the limits of our perception and consider a reality where dimensions, space, and even gravity might be illusions created by a deeper, more fundamental layer of existence. And with that, we're ready to move forward as we dive into the next theory, Kaluza-Klein theory, where the idea of a fifth dimension takes center stage in the quest to unify the forces of nature. Now, let's take a step back in time to explore a groundbreaking idea that laid the foundation for much of the modern thinking about hidden dimensions, Kaluza-Klein theory. Proposed in the early 20th century by mathematician Theodore Kaluza and later refined by physicist Oscar Klein, this theory was one of the first attempts to unify two of the fundamental forces of nature, gravity and electromagnetism. At its core, Kaluza-Klein theory introduces a bold concept, the existence of a fifth dimension, beyond the familiar three dimensions of space and one of time. This extra dimension, though invisible to us, could hold the key to understanding how gravity and electromagnetism are interconnected. The beauty of Kaluza-Klein theory lies in its simplicity and elegance. Kaluza realized that by adding a fifth dimension to Einstein's equations of general relativity, he could naturally incorporate electromagnetism into the framework. In this model, the fifth dimension is compactified, curled up so tightly that it's imperceptible at the scales we experience in everyday life. Think of it like a garden hose. From a distance, it looks like a one-dimensional line, but up close, you can see it has a circular cross-section. Similarly, the fifth dimension in Kaluza-Klein theory is so small that it's hidden from our view, yet its presence has profound implications for the forces that govern the universe. While the original Kaluza-Klein theory didn't gain widespread acceptance at the time, its ideas have experienced a resurgence in modern physics. Today, it's seen as a precursor to string theory and other higher dimensional models. The concept of compactified dimensions, central to Kaluza-Klein's framework, plays a crucial role in these contemporary theories. For instance, in string theory, the extra dimensions required to make the math work are often described as being curled up in a similar way to Kaluza-Klein's fifth dimension. This connection highlights the enduring influence of Kaluza and Klein's work, even as our understanding of the universe has evolved. One of the most fascinating aspects of Kaluza-Klein theory is how it bridges the gap between the macroscopic and microscopic worlds. By introducing a fifth dimension, it suggests that the forces we observe in our three-dimensional reality might be manifestations of a deeper, higher dimensional structure. This idea has inspired physicists to rethink the nature of space and time, leading to new insights into the unification of forces and the possibility of hidden dimensions. While the theory itself has its limitations, such as explaining why the fifth dimension is so small, it remains a cornerstone in the quest to uncover the universe's deepest secrets. As we reflect on Kaluza-Klein theory, we're reminded of the power of bold ideas to reshape our understanding of the cosmos. It's a testament to the creativity and persistence of scientists who dare to imagine the unimaginable. And with that, we're ready to move forward as we explore another intriguing concept: how gravity might be leaking into higher dimensions, offering a potential solution to one of the universe's greatest mysteries. Now, let's shift our focus to a fascinating idea that could explain one of the most puzzling aspects of our universe: why gravity is so much weaker than the other fundamental forces. This brings us to the concept of extra dimensions and how they might be influencing gravity in ways we're only beginning to understand. Imagine gravity as a force that doesn't just operate within the three dimensions of space and one of time that we're familiar with. Instead, it could be spreading out into higher dimensions, effectively diluting its strength in our observable universe. This idea, often referred to as the leaking gravity hypothesis, suggests that what we perceive as gravity's weakness might actually be a clue to the existence of hidden dimensions. To put it simply, if gravity is leaking into these extra dimensions, it would explain why it feels so much fainter compared to forces like electromagnetism or the strong nuclear force, which are confined to our familiar four-dimensional spacetime. Think of it like water seeping through a sponge. Some of it stays in the sponge, but a lot of it escapes into the surrounding space. In this analogy, the sponge represents our universe and the water is gravity, with the extra dimensions acting as the space it's leaking into. This theory isn't just a wild speculation, it has real implications for how we understand the universe. For instance, it could help explain why gravity is so much weaker than the other forces, a question that has puzzled physicists for decades. If gravity is spreading out into higher dimensions, it would naturally appear weaker in our four-dimensional world. But how do we test such a bold idea? Scientists have been working on experiments to detect these extra dimensions, often focusing on extremely small scales where the effects of higher dimensions might become noticeable. One approach involves searching for deviations in the behavior of gravity at very short distances. If gravity is leaking into extra dimensions, its strength should change in ways that differ from what Newton's or Einstein's laws predict. Another intriguing avenue is the Large Hadron Collider, the world's most powerful particle accelerator. By smashing particles together at incredibly high energies, physicists hope to create conditions where the effects of extra dimensions might reveal themselves, even if only briefly. These experiments are like peering into the cracks of reality, searching for hints of a deeper, more complex structure hidden beneath the surface. While we haven't yet found definitive evidence of extra dimensions, the search itself is pushing the boundaries of our understanding. It's a reminder that the universe is full of mysteries waiting to be uncovered, and that even the weakest force in nature might hold the key to some of its deepest secrets. As we continue our journey through the hidden dimensions of existence, let's turn our attention to another intriguing possibility: how quantum entanglement might be connected to these unseen realms, offering new insights into the strange world of quantum mechanics. Now, let's venture into one of the most mind-bending ideas in modern physics: the connection between quantum entanglement and hidden dimensions. Quantum entanglement, often called spooky action at a distance by Einstein, is the phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This strange behavior has puzzled scientists for decades, but what if hidden dimensions hold the key to understanding it? Imagine two particles entangled in a way that defies our usual understanding of space and time. Instead of their connection being limited to the three dimensions we can see, what if they're interacting through higher dimensions we can't perceive? This idea suggests that the seemingly instantaneous communication between entangled particles might not be happening across the vast distances of our observable universe, but through shortcuts in hidden dimensions. Think of it like this: if you were to draw 2 points on a piece of paper, the shortest path between them would be a straight line. But if you fold the paper, those points could suddenly touch, bypassing the distance entirely. In this analogy, the paper represents our familiar three-dimensional space, and the fold represents a hidden dimension. Entangled particles might be folding reality, using these extra dimensions to communicate instantly, even if they're light years apart in our observable universe. This theory could revolutionize our understanding of quantum mechanics. If hidden dimensions are facilitating entanglement, it would mean that the bizarre behavior of quantum particles isn't just a quirk of nature, but a sign of a deeper, more complex reality. It could also help explain why quantum mechanics seems so counterintuitive, because it's operating in a framework that includes dimensions beyond our perception. But how do we test such a radical idea? One approach involves studying the behavior of entangled particles in extreme conditions, such as near black holes or in high-energy particle collisions. If hidden dimensions are influencing entanglement, there might be subtle deviations from what quantum mechanics predicts, offering clues to their existence. Another possibility is that future advancements in quantum computing could reveal patterns or anomalies that point to the presence of these unseen dimensions. The implications of this theory are profound. Not only could it explain the mysteries of quantum entanglement, but it might also bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that have so far resisted unification. By suggesting that hidden dimensions play a role in the quantum realm, this idea opens up new avenues for exploring the fundamental nature of reality. As we continue to unravel the secrets of the universe, the possibility that hidden dimensions are shaping the quantum world reminds us that there's still so much we don't understand. And with that in mind, let's turn our attention to another fascinating theory: how hidden dimensions might be connected to the multiverse, offering a glimpse into the infinite possibilities of existence. Now, let's take a step into the vast and speculative realm of the multiverse, where hidden dimensions might hold the key to understanding the existence of countless other universes. The multiverse theory suggests that our universe is just one of many, each existing in its own dimensional slice of reality. But how do hidden dimensions fit into this picture? Imagine a loaf of bread where each slice represents a separate universe. In this analogy, the space between the slices, the gaps we can't see, could be the hidden dimensions that keep these universes apart. While we live in one slice, other universes might exist in parallel, separated by dimensions beyond our perception. This idea isn't just science fiction. It's a serious proposal in cosmology that could explain some of the biggest mysteries of our universe. For instance, why does our universe seem so finely tuned for life? If there are countless other universes, each with different physical laws and constants, it's possible that we just happen to live in one where conditions are perfect for our existence. Hidden dimensions could be the framework that allows these universes to coexist without interfering with one another, like rooms in a vast multidimensional mansion. But how do hidden dimensions enable the multiverse? One possibility is that these extra dimensions act as bridges or boundaries between universes. In some theories, collisions between membranes floating in higher dimensional space, could have sparked the Big Bang, creating our universe. If that's the case, other universes might have formed in similar ways, each occupying its own slice of the cosmic loaf. The implications of this idea are staggering. If hidden dimensions are the scaffolding of the multiverse, they could explain not only the origins of our universe but also the potential for infinite others. It could also provide a natural explanation for phenomena like dark energy, which might be the result of interactions between our universe and others through these hidden dimensions. Exploring this theory requires pushing the boundaries of both physics and imagination. While we can't yet observe other universes directly, scientists are searching for indirect evidence, such as gravitational waves or anomalies in the cosmic microwave background that might hint at their existence. Future experiments, like those involving particle accelerators or space-based observatories, could bring us closer to uncovering the truth. The multiverse and hidden dimensions remind us that reality might be far more complex and interconnected than we ever imagined. As we continue to explore these ideas, we're not just uncovering the secrets of our universe, we're peering into the infinite possibilities of existence itself. And with that, let's turn our attention to another intriguing theory: how hidden dimensions might be tied to the fine-tuning of the universe, offering a potential solution to one of cosmology's greatest puzzles. Now, let's shift our focus to a fascinating idea that might explain why we don't notice extra dimensions in our everyday lives: compactified dimensions. Imagine a garden hose stretched out across a field. From a distance, it looks like a simple one-dimensional line. But if you zoom in, you'd see that the hose actually has a circular shape with a tiny second dimension wrapped around it. This is the essence of compactified dimensions, extra dimensions that are so small and tightly curled up that they're invisible to us. In string theory, compactified dimensions play a crucial role. The theory suggests that the universe has more than the three spatial dimensions we're familiar with: height, width, and depth. But these extra dimensions aren't sprawling and expansive like the ones we know. Instead, they're incredibly tiny, perhaps as small as a billionth of the size of an atom. These compactified dimensions are thought to be curled up into intricate shapes, like the Calabi-Yau manifolds we discussed earlier, which determine the properties of particles and forces in our universe. So, why don't we notice these extra dimensions? Think of it like this: if you were an ant walking along a tightrope, you'd only experience movement along the length of the rope. The rope's thickness or any tiny imperfections in its surface would be too small for you to perceive. Similarly, compactified dimensions are so minuscule that they're beyond the reach of our current technology and senses. This concept is central to string theory because it helps explain how the universe's fundamental forces and particles could arise from the vibrations of tiny strings. The shape and size of these compactified dimensions influence how strings vibrate, which in turn determines the properties of everything from electrons to photons. Without compactified dimensions, string theory wouldn't be able to account for the diversity of particles and forces we observe in nature. However, compactified dimensions also present significant challenges. For one, we have no direct evidence that they exist. While string theory predicts their presence, they're so small that detecting them with current technology seems nearly impossible. Additionally, the mathematics involved in describing these dimensions is incredibly complex, making it difficult to test the theory or derive concrete predictions. Despite these challenges, the idea of compactified dimensions remains a cornerstone of modern theoretical physics. It offers a compelling way to reconcile the existence of extra dimensions with our everyday experience of a three-dimensional world. As scientists continue to explore this concept, they're not only pushing the boundaries of our understanding, but also opening up new possibilities for uncovering the hidden structure of reality. With this in mind, let's turn our attention to another intriguing theory: the possibility that some extra dimensions might not be tiny at all, but instead large and hidden in plain sight, offering a new perspective on the mysteries of dark energy and the cosmos. Now, let's explore a theory that flips the idea of compactified dimensions on its head: the possibility that some extra dimensions might not be tiny at all, but instead large and hidden in plain sight. This concept, known as large extra dimensions, challenges our understanding of space and could hold the key to explaining one of the universe's greatest mysteries, dark energy. Unlike compactified dimensions, which are curled up so small that they're invisible, large extra dimensions propose that some dimensions might be vast, extending far beyond what we can perceive. Imagine living on the surface of a sheet of paper. To you, the world appears flat and two-dimensional. But if someone lifted the paper into the air, revealing its thickness, you'd suddenly realize there's a third dimension you couldn't see before. Large extra dimensions suggest something similar. Our universe might be embedded in a higher dimensional space, with these extra dimensions stretching out in ways we can't detect directly. So, why don't we notice these large extra dimensions? One possibility is that the forces and particles we're familiar with, like gravity, light, and matter, are confined to our three-dimensional brain or slice of reality. Meanwhile, other forces or particles might exist in these higher dimensions, interacting with our universe in subtle ways. This idea could explain why gravity, for example, appears so weak compared to other forces. If gravity leaks into these large extra dimensions, its strength would be diluted, making it seem weaker in our three-dimensional world. But how does this connect to dark energy? Dark energy is the mysterious force driving the accelerated expansion of the universe, and its nature remains one of the biggest puzzles in cosmology. Some theories suggest that dark energy could be a manifestation of these large extra dimensions. If our universe is embedded in a higher dimensional space, the energy of that space might influence the expansion of our own dimensions, creating the effect we observe as dark energy. This idea is still speculative, but it offers a tantalizing possibility. The hidden structure of the universe might not just be about tiny, curled-up dimensions, but also vast, unseen ones that shape the cosmos in profound ways. While we don't yet have direct evidence for large extra dimensions, their existence could revolutionize our understanding of space, gravity, and the forces that govern the universe. As we continue to probe the mysteries of dark energy and the hidden dimensions of existence, theories like this remind us that the universe is far stranger and more complex than we can imagine. And with that, let's turn our attention to another intriguing idea: the possibility that dark matter itself might reside in these hidden dimensions, interacting with our universe in ways we're only beginning to understand. Now, let's venture into a theory that ties the mysterious nature of dark matter to the hidden dimensions we've been exploring. Dark matter, the invisible substance that makes up a significant portion of the universe's mass, has long puzzled scientists. It doesn't emit light or interact with electromagnetic forces, yet its gravitational effects are undeniable. So, what if dark matter isn't just hiding in plain sight, but exists in dimensions beyond our own? This idea proposes that dark matter particles might reside in these hidden dimensions, interacting with our universe primarily through gravity. Think of it like this: if our three-dimensional world is a stage, dark matter could be the actors moving behind the scenes in higher dimensional spaces. While we can't see them directly, their presence influences the performance on stage, our observable universe. One of the most compelling aspects of this theory is how it could explain why dark matter is so elusive. If dark matter exists in higher dimensions, it wouldn't interact with the particles and forces we're familiar with in our three-dimensional world. Gravity, however, could act as a bridge between these dimensions, allowing dark matter to exert its influence on our universe without being directly detectable. This concept also opens up new possibilities for understanding the distribution of dark matter. Observations show that dark matter forms vast halos around galaxies, shaping their structure and movement. If dark matter resides in hidden dimensions, its distribution could be influenced by the geometry of those dimensions, offering a fresh perspective on how these halos form and evolve. While this theory is still speculative, it provides a fascinating framework for exploring the nature of dark matter. It challenges us to think beyond the confines of our three-dimensional experience and consider how the hidden dimensions of existence might hold the key to solving one of the universe's greatest mysteries. As we continue to unravel the secrets of dark matter and hidden dimensions, theories like this remind us that the universe is full of surprises waiting to be discovered. And with that, let's shift our focus to another intriguing idea: the possibility that time itself could be a higher dimensional construct, offering new insights into the flow of causality and the nature of existence. Now, let's turn our attention to a theory that challenges our very understanding of time itself. What if time, the steady, one-way flow we experience every day, is not just a linear progression but a higher dimensional construct? This idea suggests that time might be far more complex than we realize, woven into the fabric of hidden dimensions that shape our reality. Imagine time not as a straight line but as a multi-layered tapestry, with each thread representing a different dimension. In this view, the flow of time we perceive could be just one slice of a much larger, interconnected structure. This raises fascinating questions about causality, the relationship between cause and effect. If time exists in higher dimensions, could events in our universe be influenced by interactions in these hidden layers? One intriguing possibility is that higher dimensional time could explain phenomena like time dilation, where time appears to slow down or speed up depending on gravity or velocity. If time is a higher dimensional construct, these effects might be the result of our limited perspective, like trying to understand a three-dimensional object by looking at its shadow. This theory also opens the door to rethinking the arrow of time, the idea that time moves in one direction from past to future. In higher dimensions, the arrow of time might not be so straightforward. Some physicists speculate that in these hidden layers, time could flow in multiple directions or even loop back on itself, creating possibilities for alternate timelines or parallel universes. While this concept is still speculative, it offers a fresh lens through which to explore the mysteries of time. It challenges us to think beyond the linear flow we're accustomed to and consider how hidden dimensions might shape the very fabric of existence. As we ponder these ideas, we're reminded that the universe is far stranger and more intricate than we often imagine. And with that, let's move on to another captivating theory: the role hidden dimensions might play in the enigmatic nature of black holes and their singularities. Now let's venture into the mysterious depths of black holes, where the fabric of space and time bends to its limits. Black holes have long fascinated scientists and dreamers alike, but what if these cosmic giants are more than just gravitational traps? What if they are gateways to hidden dimensions, offering a passage to realms beyond our comprehension? At the heart of every black hole lies a singularity, a point where gravity becomes infinitely strong and the laws of physics as we know them break down. In this extreme environment, the very nature of space and time is warped beyond recognition. Some theories suggest that these singularities might not just be endpoints but portals, connecting our universe to higher dimensional spaces. Imagine a black hole as a cosmic tunnel with its singularity acting as a doorway. If hidden dimensions exist, they could be accessible through these gateways, allowing matter and energy to traverse into entirely different realms. This idea aligns with the concept of wormholes, hypothetical passages through spacetime that could connect distant points in the universe or even different universes altogether. But how could this work? One possibility is that the intense gravitational forces within a black hole stretch and twist spacetime to such an extent that it creates a bridge to higher dimensions. In this scenario, the singularity isn't a dead end but a transition point where the rules of our three-dimensional world no longer apply. This theory also raises intriguing questions about the fate of matter that falls into a black hole. Instead of being crushed into oblivion, could it be transported to another dimension or universe? Some physicists speculate that black holes might not destroy information, but instead encode it in higher dimensional structures, preserving it in ways we can't yet understand. While these ideas remain speculative, they challenge us to rethink the nature of black holes and their role in the cosmos. Could these enigmatic objects be the key to unlocking the secrets of hidden dimensions? As we continue to explore the universe's most extreme phenomena, black holes may hold the answers to some of our deepest questions about existence itself. With this in mind, let's turn our attention to another fascinating theory: the connection between hidden dimensions and the very fabric of consciousness, where science and philosophy intertwine in unexpected ways. Now, let's take a step into the realm where science meets philosophy, exploring the intriguing possibility that consciousness itself might be intertwined with hidden dimensions. What if our thoughts, perceptions, and sense of self are not confined to the three-dimensional world we experience? What if consciousness extends beyond the boundaries of our known reality, tapping into dimensions we cannot yet perceive? This theory suggests that hidden dimensions could play a role in shaping the very nature of consciousness. Imagine consciousness as a multi-layered phenomenon, with some aspects existing in higher dimensional spaces. In this view, our awareness might not be limited to the physical brain, but could be influenced by interactions with these unseen dimensions. One way to think about this is through the lens of quantum mechanics. At the quantum level, particles can exist in multiple states simultaneously, a phenomenon known as superposition. Some scientists propose that consciousness might operate in a similar way, accessing higher dimensional information that our physical senses cannot detect. This could explain why human consciousness feels so vast and complex, as if it's connected to something greater than the material world. Another angle to consider is the idea that hidden dimensions could act as a medium for consciousness to interact with the universe. Just as gravity might leak into higher dimensions, as we discussed earlier, consciousness could also have a presence in these unseen realms. This would mean that our thoughts and perceptions are not entirely bound by the physical brain, but are part of a larger, multi-dimensional network. This theory also opens the door to philosophical questions about the nature of reality and existence. If consciousness is influenced by hidden dimensions, does that mean our understanding of reality is incomplete? Could there be entire layers of existence that we are unaware of, yet still connected to through our consciousness? While this idea remains speculative, it challenges us to think beyond the limits of our current scientific understanding. It invites us to consider that consciousness might be more than just a product of the brain. It could be a bridge to the hidden dimensions of the universe. As we ponder these profound questions, let's shift our focus to another captivating theory: the possibility that hidden dimensions could allow for parallel universes to exist alongside our own, with interactions occurring through higher dimensional bridges. Now let's venture into a theory that stretches the boundaries of imagination: parallel universes and their connection to hidden dimensions. What if our universe is just one of many, coexisting in a vast multi-dimensional tapestry? This idea suggests that hidden dimensions could serve as bridges, linking our reality to countless others, each with its own unique set of physical laws and possibilities. Imagine hidden dimensions as invisible highways connecting parallel universes that exist alongside our own. These higher dimensional bridges could allow for interactions between universes, even if we're unable to perceive them directly. For instance, particles or forces from one universe might influence another through these unseen pathways, creating subtle but detectable effects in our own reality. One way to visualize this is through the concept of brains, which we explored earlier. If our universe is a three-dimensional brain floating in a higher dimensional space, other brains representing parallel universes could exist nearby. Interactions between these brains might occur through hidden dimensions, leading to phenomena that challenge our understanding of physics. This theory also ties into the idea of the multiverse, where every possible outcome of an event exists in a separate universe. Hidden dimensions could provide the framework for this infinite array of realities, acting as the glue that holds the multiverse together. For example, a decision you make in this universe might play out differently in another, with each outcome unfolding in its own dimensional slice. But how could we ever detect these parallel universes? Some scientists propose that gravitational waves or quantum anomalies might hold clues. If gravity can leak into higher dimensions, as we've discussed, it's possible that interactions between parallel universes could leave faint imprints in our own. These imprints might appear as unexplained fluctuations in energy or strange patterns in cosmic background radiation. This theory doesn't just expand our understanding of the cosmos, it also raises profound questions about existence itself. If parallel universes exist, does that mean every version of you is out there somewhere? Could we ever communicate or travel between these realities? While these questions remain unanswered, they inspire us to think beyond the confines of our own universe and explore the limitless possibilities of hidden dimensions. As we wrap up this exploration of parallel universes, let's turn our attention to another fascinating idea: the role hidden dimensions might have played in the Big Bang and how they could hold the key to understanding the very origins of our universe. Now let's take a step back in time, way back to the very beginning of everything. What if the Big Bang, the event that birthed our universe, wasn't just a singular explosion but the result of something far more complex happening in higher dimensions? This theory proposes that the Big Bang might have been a collision between branes, those multidimensional membranes we've discussed earlier, in a higher dimensional space. Picture this: two branes, each representing a universe floating in a higher dimensional realm. When these branes collide, the energy released could be so immense that it triggers the creation of an entirely new universe, our universe. This idea, known as the brane collision theory, suggests that the Big Bang wasn't an isolated event but rather a cosmic collision in a much larger, hidden dimensional framework. But why would such a collision create a universe? Think of it like ripples on the surface of a pond. When two objects collide in water, they create waves that spread outward. In the same way, the collision of branes in higher dimensions could generate waves of energy, which then expand and cool, forming the building blocks of matter and space-time as we know it. This process could explain not only the Big Bang, but also the uniformity and structure we observe in the universe today. This theory also ties into the concept of cyclic universes, where the Big Bang isn't a one-time event but part of an endless cycle of collisions and expansions. In this model, our universe might be just one in a series, with each collision between branes sparking a new cosmic beginning. It's a mind-bending idea that challenges our understanding of time and existence, suggesting that the universe might be far more dynamic and interconnected than we ever imagined. So, how could we test this idea? Some scientists believe that gravitational waves, those ripples in space-time caused by massive cosmic events, might hold clues. If the Big Bang was indeed a brane collision, it could have left behind a unique signature in the gravitational wave background, a faint echo of that primordial event. Detecting such a signal would be groundbreaking, offering us a glimpse into the hidden dimensions that shaped our universe's birth. As we ponder the origins of everything, this theory invites us to consider the possibility that our universe is just one piece of a much larger, multidimensional puzzle. It's a reminder that the mysteries of existence might extend far beyond what we can see or measure, hidden in dimensions we're only beginning to imagine. With this cosmic collision in mind, let's shift our focus to another intriguing question: how hidden dimensions might explain the fine-tuning of the universe's constants, and whether they hold the key to solving one of cosmology's greatest puzzles. Now, let's turn our attention to one of the most puzzling questions in cosmology. Why does our universe seem so perfectly fine-tuned for life? This is known as the fine-tuning problem, and it's a mystery that has baffled scientists for decades. The constants of nature, like the strength of gravity, the speed of light, and the mass of elementary particles, are precisely set in a way that allows stars, planets, and ultimately life to exist. If any of these values were even slightly different, the universe as we know it wouldn't exist. So, how do hidden dimensions fit into this picture? One compelling idea is that hidden dimensions could provide a natural explanation for this fine-tuning. Imagine that the constants we observe in our three-dimensional universe are actually influenced by the geometry and dynamics of higher dimensions. In this scenario, the values of these constants aren't arbitrary, but are instead determined by the underlying structure of the hidden dimensions. For example, the way extra dimensions are compactified or curled up could dictate the strength of forces like gravity or electromagnetism in our observable universe. This would mean that the fine-tuning isn't a coincidence but a consequence of the universe's higher dimensional architecture. Another possibility is that hidden dimensions allow for a multiverse, a vast collection of universes, each with its own set of physical constants. In this multiverse, most universes might have constants that don't support life, but a small fraction, like ours, could have just the right conditions. Hidden dimensions could act as the framework that allows these universes to coexist, with each one occupying a different slice of the higher dimensional space. This would mean that our universe's fine-tuning isn't special or unique, but simply one of many possible outcomes in a much larger cosmic landscape. But how could we test these ideas? One approach is to look for evidence of hidden dimensions in the behavior of particles or forces. For instance, if gravity is leaking into higher dimensions, as some theories suggest, it could leave subtle imprints in experiments designed to measure its strength at very small scales. Similarly, if the compactified dimensions influence the constants of nature, their effects might be detectable through precise measurements of particle interactions or cosmological observations. This theory not only offers a potential solution to the fine-tuning problem, but also deepens our understanding of the universe's underlying structure. It suggests that the constants we observe might be clues to the hidden dimensions that shape reality, offering a glimpse into the deeper layers of existence. As we continue to explore these ideas, we're reminded that the universe's mysteries might not be confined to the dimensions we can see, but could extend into realms we're only beginning to imagine. With this in mind, let's move forward to explore how hidden dimensions might play a role in unifying quantum mechanics and general relativity, two of the most fundamental yet seemingly incompatible theories in physics. Now, let's shift our focus to one of the most profound challenges in modern physics, the quest to unify quantum mechanics and general relativity. These two pillars of physics describe the universe in fundamentally different ways. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity explains the force of gravity and the structure of space-time on cosmic scales. Yet, despite their individual successes, these theories remain stubbornly incompatible. Hidden dimensions might just hold the key to bridging this divide. Imagine if the fabric of space-time isn't just the four dimensions we experience, three of space and one of time, but is instead woven from a higher dimensional tapestry. Hidden dimensions could provide the framework needed to reconcile quantum mechanics and general relativity. For instance, string theory suggests that particles aren't point-like objects but tiny, vibrating strings existing in higher dimensions. These vibrations could account for both the quantum behavior of particles and the curvature of space-time described by general relativity, offering a unified description of reality. One intriguing possibility is that gravity, which appears weak in our four-dimensional universe, might actually be a much stronger force when viewed in the context of higher dimensions. In this scenario, gravity's apparent weakness could be due to its spreading out into these extra dimensions, diluting its strength in our observable universe. This idea not only explains why gravity is so much weaker than the other fundamental forces, but also provides a pathway to unify it with quantum mechanics. By extending our understanding of gravity into higher dimensions, we might finally uncover the quantum nature of gravity itself, Another angle involves the concept of branes, membranes existing in higher dimensional space. In some theories, our universe could be a three-dimensional brane floating within a higher dimensional bulk. Gravity, unlike other forces, might be able to traverse this bulk, interacting with other branes or dimensions in ways that could explain its unique behavior. This could lead to a deeper understanding of how gravity operates at both quantum and cosmic scales, potentially resolving the inconsistencies between the two theories. But how do we test these ideas? Experimental efforts are already underway. For example, particle accelerators like the Large Hadron Collider are searching for evidence of extra dimensions by looking for tiny deviations in particle behavior or the production of exotic particles that could hint at higher dimensional interactions. Similarly, gravitational wave detectors might one day reveal subtle signatures of hidden dimensions in the ripples of space-time caused by cataclysmic events like black hole mergers. Hidden dimensions offer a tantalizing possibility that the unification of quantum mechanics and general relativity isn't just a dream but a reality waiting to be uncovered. By exploring these higher dimensional frameworks, we're not only addressing one of physics' greatest challenges, but also opening the door to a deeper understanding of the universe's fundamental nature. As we continue to probe these ideas, we're reminded that the answers to some of our biggest questions might lie in dimensions we've yet to fully comprehend. With this in mind, let's now explore how hidden dimensions might redefine our understanding of reality itself, blurring the lines between science and metaphysics. Now, let's take a step into the realm of the profound and the speculative. Hidden dimensions don't just challenge our understanding of physics, they might fundamentally reshape how we perceive reality itself. What if the world we see, touch, and experience is only a fraction of what truly exists? What if hidden dimensions are the missing pieces that connect the tangible with the intangible, the scientific with the metaphysical? Consider this: our perception of reality is limited by the dimensions we can observe. We live in a world of three spatial dimensions and one of time, but what if there's more? Hidden dimensions could mean that what we consider real is just a slice of a much larger, more complex existence. For instance, imagine a two-dimensional being living on a flat plane. To them, a three-dimensional object passing through their world would appear as a series of incomprehensible, shifting shapes. In the same way, higher dimensional phenomena might be influencing our reality in ways we can't fully grasp, manifesting as strange or unexplained events. This idea blurs the line between science and metaphysics. If hidden dimensions exist, they could explain phenomena that currently defy conventional understanding, such as consciousness, intuition, or even the nature of existence itself. Some theories suggest that consciousness might not be confined to the physical brain, but could extend into higher dimensions, interacting with a broader, multidimensional reality. This would mean that our thoughts, emotions, and perceptions might be influenced by forces beyond our four-dimensional experience. Moreover, hidden dimensions could redefine the concept of space and time. What if time isn't a linear progression but a higher dimensional construct? In this view, past, present, and future might coexist in a multidimensional framework, with hidden dimensions acting as the threads that weave them together. This could offer new insights into phenomena like déjà vu, precognition, or even the nature of free will. But let's not stop there. Hidden dimensions might also challenge our understanding of causality, the idea that every effect has a cause. In a higher dimensional reality, cause and effect might not follow the straightforward rules we're used to. Events in our universe could be influenced by interactions in hidden dimensions, creating a web of connections that defy our current logic. Of course, these ideas venture into the speculative, but that's where the beauty lies. Hidden dimensions invite us to question the very nature of reality, pushing the boundaries of science and philosophy. They remind us that the universe is far stranger and more mysterious than we can imagine. and that our understanding of it is still in its infancy. As we ponder these possibilities, we're left with a tantalizing question. Could hidden dimensions be the key to unlocking the deepest mysteries of existence? The answer might lie in dimensions we've yet to explore, waiting to reveal a reality far more intricate and interconnected than we've ever dreamed. And with that, let's turn our attention to how hidden dimensions might influence the speed of light, offering new insights into the universe's expansion. Now, let's shift our focus to a fascinating intersection of hidden dimensions and one of the most fundamental constants in physics, the speed of light. What if the speed of light, which we've long considered an unbreakable cosmic speed limit, isn't as constant as we think? What if it behaves differently in higher dimensions, offering us a new lens through which to understand the universe's expansion? In our familiar four-dimensional space-time, the speed of light is a fixed value, approximately 299,792 kilometers per second. This constant underpins much of modern physics, from Einstein's theory of relativity to our understanding of how the universe operates. But what if this speed isn't universal? Some theories suggest that in higher dimensions, the speed of light could vary, potentially explaining phenomena that currently baffle scientists. Imagine for a moment that light travels faster or slower in hidden dimensions. This variation could have profound implications for how we perceive the universe's expansion. For instance, if light moves more quickly in higher dimensions, it might help explain why distant galaxies appear to be receding from us at accelerating rates, a phenomenon often attributed to dark energy. Could it be that what we interpret as dark energy is actually the influence of hidden dimensions altering the behavior of light? Another intriguing possibility is that the speed of light in higher dimensions could affect the way information travels across the cosmos. If light can traverse hidden dimensions more efficiently, it might create shortcuts through space-time, allowing information to reach us in ways that seem to defy our current understanding of physics. This could shed light on mysteries like quantum entanglement, where particles appear to communicate instantaneously across vast distances, seemingly bypassing the speed of light. But how would we detect such variations? One approach involves studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. If the speed of light in higher dimensions leaves subtle imprints on this radiation, scientists might be able to uncover evidence of these hidden realms. Similarly, experiments with particle accelerators could reveal anomalies in the behavior of light or other particles, hinting at the presence of extra dimensions. This idea also opens up new questions about the nature of space-time itself. If the speed of light isn't constant across all dimensions, does that mean space-time is more fluid and dynamic than we've assumed? Could hidden dimensions act as a kind of cosmic fabric, stretching and bending in ways that influence the flow of light and, by extension, the structure of the universe? As we explore these possibilities, we're reminded once again of how much we still have to learn about the cosmos. Hidden dimensions challenge us to rethink even the most fundamental aspects of physics, offering tantalizing clues about the true nature of reality. And with that, let's turn our attention to how hidden dimensions might shape the arrow of time, unraveling the mysteries of its one-way flow. Now, let's venture into a realm where hidden dimensions might hold the key to one of the most puzzling aspects of our universe, the arrow of time. Why does time flow in one direction from past to future and never the other way around? Could hidden dimensions be the reason behind this irreversible flow? In our everyday experience, time feels like a straight line moving us forward from one moment to the next. But in the grand scheme of the cosmos, time's one-way nature is a mystery that has puzzled scientists for centuries. Hidden dimensions might offer a fresh perspective on this enigma. Imagine that time, as we perceive it, is just a slice of a much larger, multidimensional structure. In higher dimensions, time might not be linear at all. It could loop, twist, or even branch in ways that are invisible to us. One intriguing idea is that the arrow of time is shaped by the geometry of hidden dimensions. Just as gravity warps spacetime in our four-dimensional universe, higher dimensions could influence how time flows. For instance, if hidden dimensions are asymmetrical or have a specific curvature, they might create a natural directionality to time, explaining why it moves forward and not backward. This could also help us understand why certain processes, like the mixing of cream into coffee or the breaking of an egg, are irreversible. They might be tied to the underlying structure of these hidden realms. Another possibility is that hidden dimensions act as a kind of cosmic filter, allowing time to flow in one direction while blocking any backward movement. This could explain why we remember the past but not the future, and why entropy, the measure of disorder in a system, always increases over time. If hidden dimensions are influencing entropy, they might be the reason why the universe tends toward chaos rather than order. But how could we test these ideas? One approach involves studying the behavior of particles at the quantum level, where the rules of time seem to blur. If hidden dimensions are affecting the flow of time, they might leave subtle traces in quantum systems, such as anomalies in particle decay rates or unexpected patterns in quantum entanglement. Additionally, cosmological observations, like the distribution of galaxies or the properties of the cosmic microwave background, might reveal clues about how hidden dimensions shape the arrow of time. This exploration of time and hidden dimensions not only deepens our understanding of the universe, but also challenges us to rethink our place within it. If time's flow is tied to higher dimensional structures, what does that mean for our perception of reality? Could it open the door to new ways of thinking about causality, memory, and even the nature of existence itself? As we ponder these questions, we're reminded that the mysteries of time and hidden dimensions are deeply intertwined, offering us a glimpse into the profound complexity of the cosmos. And with that, let's turn our attention to another fascinating intersection of hidden dimensions and one of the universe's greatest puzzles, the Fermi paradox. Now let's shift our gaze to one of the most perplexing questions in science, the Fermi paradox. If the universe is so vast and filled with countless stars and planets, why haven't we encountered any signs of extraterrestrial life? Could hidden dimensions hold the answer to this cosmic silence? The Fermi paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of alien civilizations existing and the complete lack of evidence for their existence. One intriguing possibility is that advanced civilizations might not be absent. They could simply exist in dimensions beyond our perception. Imagine a universe where intelligent life thrives in higher dimensional spaces, completely invisible and inaccessible to us. These civilizations might be all around us, yet separated by the fabric of hidden dimensions, making contact impossible with our current understanding of physics. If hidden dimensions are real, they could provide a natural explanation for why we haven't detected extraterrestrial signals or visited by alien spacecraft. Advanced beings might have evolved to interact with these higher dimensions, using them for travel, communication, or even survival. For example, a civilization in a five-dimensional space could bypass the limitations of our three-dimensional universe, making interstellar travel trivial. To them, our universe might appear flat and constrained, much like how a two-dimensional world would seem to us. Another fascinating angle is that hidden dimensions could act as a kind of cosmic barrier, preventing civilizations from different dimensional realms from interacting. Just as we can't perceive or touch objects in higher dimensions, alien life forms might be unable to reach us, even if they wanted to. This could explain why, despite the vastness of the cosmos, we remain isolated. It's not that the universe is empty, it's that we're looking in the wrong dimensions. But how could we test this idea? One approach involves searching for anomalies in the behavior of particles or energy that might hint at interactions with higher dimensions. For instance, if alien civilizations are using hidden dimensions for communication, they might leave behind subtle traces in the form of unexplained energy patterns or gravitational waves. Additionally, advancements in quantum physics and cosmology could one day provide the tools needed to detect these higher dimensional realms, potentially revealing the presence of extraterrestrial life. This theory not only offers a fresh perspective on the Fermi paradox, but also challenges us to expand our understanding of existence. If hidden dimensions are home to advanced civilizations, what does that mean for our place in the universe? Could we one day unlock the secrets of these dimensions and make contact with beings from beyond our reality? As we explore these possibilities, we're reminded that the universe is far more mysterious and complex than we can imagine. Hidden dimensions might not just be a scientific curiosity. They could be the key to solving one of the greatest mysteries of all, the silence of the cosmos. And with that, let's turn our attention to another captivating intersection of hidden dimensions and the nature of reality, the simulation hypothesis. Now, let's venture into a theory that blurs the line between science and philosophy, the simulation hypothesis. Could our universe be a highly advanced simulation? And if so, might hidden dimensions serve as the underlying framework that makes it all possible? This idea, once confined to science fiction, has gained traction among scientists and thinkers who ponder the nature of reality. The simulation hypothesis suggests that our universe, with all its complexity, might be an artificial construct, a kind of cosmic computer program. But what if the code running this simulation exists in higher dimensions? Hidden dimensions could act as the unseen infrastructure, the blueprint that governs the laws of physics, the flow of time, and even the behavior of particles in our perceived reality. In this view, the three-dimensional world we experience is merely the output of a much more intricate, multi-dimensional system. Think of it like this. If our universe is a video game, the hidden dimensions could be the programming language and algorithms that make the game function. Just as a game developer uses code to create a virtual world, a higher dimensional intelligence might use these extra dimensions to design and sustain our reality. This raises profound questions. Are we living in a simulated universe? And if so, who or what is running the simulation? Could hidden dimensions hold the answers? One compelling argument for this idea comes from the peculiar behavior of quantum particles. At the quantum level, particles seem to defy the rules of our three-dimensional world, appearing and disappearing in ways that suggest they're interacting with something beyond our perception. Some scientists speculate that these anomalies could be evidence of a higher dimensional framework influencing our reality. If true, this would mean that the glitches we observe in quantum mechanics are not errors but features of the simulation, revealing glimpses of the code behind the cosmos. Moreover, hidden dimensions could explain why the universe appears so finely tuned for life. If our reality is a simulation, the precise constants and laws of physics might be the result of intentional design, with higher dimensions serving as the control panel for these settings. This would provide a natural explanation for the fine-tuning problem, suggesting that our universe is not a random accident but a carefully crafted construct. But how could we test such a radical idea? Some researchers propose that if our universe is a simulation, there might be detectable limits to its resolution, tiny pixels of space or time that reveal the underlying code. Others suggest that anomalies in cosmic rays or quantum experiments could provide clues. While these ideas are speculative, they challenge us to rethink our understanding of reality and consider the possibility that hidden dimensions are not just a scientific curiosity but the very foundation of existence. As we explore this theory, we're left with a tantalizing question. If hidden dimensions are the code behind our reality, what does that mean for our understanding of consciousness, free will, and the nature of existence itself? Could we one day uncover the secrets of these dimensions and glimpse the true nature of the universe? With this mind-bending possibility in mind, let's turn our attention to another fascinating intersection of hidden dimensions and the fabric of reality, the nature of space itself. Now, let's shift our focus to a theory that challenges the very fabric of what we consider space to be. Hidden dimensions might not just be an abstract concept, they could fundamentally alter our understanding of space itself. What if space isn't the static, empty void we imagine, but a dynamic, multi-layered construct shaped by dimensions we can't perceive? Traditionally, space is thought of as a three-dimensional stage where everything unfolds a backdrop for the universe's events. But hidden dimensions suggest that space could be far more complex. Imagine space as a multi-dimensional tapestry woven with threads we can't see. These extra dimensions could influence how space behaves, creating layers of structure that go beyond our everyday experience. One way to think about this is through the lens of string theory, which proposes that the fundamental building blocks of the universe are tiny, vibrating strings. These strings don't just exist in the three dimensions we know, they move through higher dimensions, shaping the properties of space itself. In this view, space isn't just empty, it's a vibrant, dynamic field influenced by these hidden dimensions. But how does this change our understanding of space? For one, it suggests that space might not be uniform. Hidden dimensions could create variations in the fabric of space, leading to regions where the laws of physics behave differently. This could explain phenomena like dark energy, which seems to be causing the universe to expand at an accelerating rate. Perhaps dark energy isn't a mysterious force but a manifestation of space's multi-dimensional nature. Another intriguing possibility is that hidden dimensions could allow for shortcuts through space. Imagine folding a piece of paper so that two distant points touch. This is the idea behind wormholes, hypothetical tunnels through space-time. If hidden dimensions exist, they might make such shortcuts possible, enabling travel across vast cosmic distances in an instant. While this remains speculative, it opens up exciting possibilities for how we might one day navigate the universe. Moreover, hidden dimensions could redefine our understanding of distance and scale. In a multi-dimensional space, what we perceive as vast distances in three dimensions might be much smaller when viewed through the lens of higher dimensions. This could revolutionize our approach to cosmology, offering new ways to interpret the structure and evolution of the universe. As we explore this theory, we're left with a profound question. If space is a dynamic, multi-layered construct shaped by hidden dimensions, what does that mean for our place in the cosmos? Could understanding these dimensions unlock new ways to explore and interact with the universe? With this thought in mind, let's turn our attention to another captivating idea: the role hidden dimensions might play in the ultimate fate of the universe. Now, let's venture into a theory that takes us to the very edge of cosmic existence, the idea that hidden dimensions could hold the key to understanding the ultimate fate of the universe. What if the end of everything we know isn't just a matter of time and space as we understand them, but is deeply intertwined with dimensions beyond our perception? Traditionally, the fate of the universe has been framed by two possibilities: the Big Crunch, where everything collapses back into a singularity, or the Big Freeze, where the universe expands endlessly into a cold, dark void. But hidden dimensions introduce a third, more intriguing possibility. These unseen layers of reality could influence how the universe evolves, potentially altering its trajectory in ways we're only beginning to imagine. One compelling theory suggests that hidden dimensions might be responsible for the mysterious force driving the universe's accelerated expansion: dark energy. If dark energy is a manifestation of higher dimensional interactions, it could mean that the universe's expansion isn't just a three-dimensional phenomenon. Instead, it might be shaped by forces operating in dimensions we can't directly observe. This could lead to scenarios where the universe doesn't simply fade into darkness but undergoes a dramatic transformation, perhaps even collapsing into a higher dimensional state. Another possibility is that hidden dimensions could trigger a cosmic phase transition. Just as water turns to ice under the right conditions, the universe might undergo a sudden shift in its fundamental structure, driven by changes in higher dimensional space. This could result in a radical reconfiguration of reality, where the laws of physics as we know them no longer apply. Such an event could mark the end of our universe as we understand it, giving rise to an entirely new cosmic order. There's also the tantalizing idea that hidden dimensions could allow for the existence of parallel universes, each with its own fate. If our universe is just one of many, its end might not be the final chapter but part of a larger, multi-dimensional story. In this scenario, the collapse or transformation of our universe could be balanced by the birth or expansion of others, creating an eternal cycle of cosmic renewal. As we ponder these theories, we're left with a profound question. If hidden dimensions are shaping the universe's destiny, could they also offer a way to escape its end? Could advanced civilizations harness these dimensions to transcend the limitations of our universe, ensuring their survival even as the cosmos itself reaches its conclusion? With these possibilities in mind, we're reminded that the universe's hidden dimensions aren't just a scientific curiosity. They could hold the answers to some of the most profound questions about existence itself. And as we continue to explore these ideas, we're drawn to the next mystery, the role hidden dimensions might have played in the origin of life. Now, let's shift our focus to a theory that bridges the gap between the cosmos and the very essence of life itself. Could hidden dimensions have played a role in the origin of life? This idea takes us beyond the familiar realms of biology and chemistry, suggesting that the complexity of life might be rooted in the unseen layers of reality. Imagine for a moment that the building blocks of life, molecules, proteins, and even the intricate processes of DNA are influenced by forces operating in higher dimensions. If hidden dimensions exist, they could provide a framework for the fine-tuning of the universe's constants, creating the precise conditions necessary for life to emerge. This would mean that life isn't just a random occurrence in a vast, indifferent universe, but rather a phenomenon deeply connected to the multidimensional fabric of reality. One intriguing possibility is that hidden dimensions could act as a kind of cosmic blueprint, guiding the formation of complex structures at the molecular level. Just as a higher dimensional object casts a shadow in our three-dimensional world, the processes that give rise to life might be projections of interactions occurring in these unseen dimensions. This could explain why life seems to defy the odds, emerging in a universe that appears finely tuned for its existence. Another angle to consider is the role of quantum mechanics in the origin of life. Quantum processes, which are notoriously difficult to explain within our three-dimensional framework, might find a natural explanation in higher dimensions. For instance, the phenomenon of quantum tunneling, where particles seemingly jump through barriers, could be facilitated by interactions in hidden dimensions. If life's earliest chemical reactions relied on such quantum effects, hidden dimensions might have been the unseen architects of life's emergence. There's also the fascinating idea that hidden dimensions could allow for the existence of life in forms we can't yet comprehend. If life can exist in higher dimensional spaces, it might take on entirely different characteristics, challenging our understanding of what it means to be alive. This opens up the possibility that life isn't confined to our three-dimensional world but could thrive in realms beyond our perception. As we explore these theories, we're left with a profound question. If hidden dimensions played a role in the origin of life, could they also hold the key to understanding its ultimate purpose? Could the complexity of life be a reflection of the universe's multidimensional nature, hinting at a deeper connection between the cosmos and the living beings within it? With these possibilities in mind, we're reminded that the mysteries of life and the universe are deeply intertwined. And as we continue to unravel these connections, we're drawn to the next mystery, the limits of human perception and how they shape our understanding of the cosmos. Now, let's turn our attention to a theory that challenges the very way we perceive reality. Hidden dimensions, if they exist, might be completely beyond our ability to detect or comprehend. This raises a fascinating question. How much of the universe remains hidden from us simply because our senses and tools are limited to 3 dimensions? Consider this: throughout history, humanity's understanding of the cosmos has been shaped by the tools and frameworks available at the time. For centuries, people believed the Earth was the center of the universe, not because they were wrong, but because their observations were limited by the technology and knowledge of their era. It wasn't until the invention of the telescope that we began to see the true scale of the cosmos. Similarly, our current inability to perceive hidden dimensions might be a limitation of our tools and our senses, not a reflection of what's truly out there. Think about how much of the electromagnetic spectrum is invisible to us. We can't see ultraviolet light or radio waves, yet we know they exist because we've built instruments to detect them. Could hidden dimensions be like this, entire layers of reality, operating just beyond the reach of our perception, waiting for the right tools or theories to reveal them? This idea isn't just speculative, it's rooted in the history of science. Every major breakthrough in our understanding of the universe has come from expanding the boundaries of what we can observe and measure. From Newton's laws of motion to Einstein's theory of relativity, each revolution in science has shown us that the universe is far more complex and interconnected than we previously imagined. Hidden dimensions could be the next frontier in this ongoing journey of discovery. But here's the catch: even if hidden dimensions exist, our brains might not be equipped to fully grasp them. Our perception is hardwired for a 3-dimensional world, and trying to imagine higher dimensions is like asking a flat, 2-dimensional being to understand depth. It's not just a matter of building better tools, it's about rethinking the very way we conceptualize reality. This limitation isn't just a scientific challenge, it's a philosophical one. It forces us to confront the possibility that there are aspects of the universe that we may never fully understand. And yet, this uncertainty is also what makes science so exciting. It reminds us that the universe is full of mysteries waiting to be uncovered, and that every answer we find only leads to more questions. As we ponder the limits of human perception, we're reminded of how far we've come and how much further we have to go. The search for hidden dimensions isn't just about uncovering new layers of reality. It's about pushing the boundaries of what it means to explore, to discover, and to understand. And with that, we move closer to the next mystery, the search for extraterrestrial intelligence and how hidden dimensions might influence our quest to find life beyond Earth. Now, let's shift our focus to a question that has captivated humanity for centuries. Are we alone in the universe? The search for extraterrestrial intelligence, or SETI, has long been a cornerstone of our curiosity about the cosmos. But what if the reason we haven't found alien life yet isn't because it doesn't exist, but because it exists in dimensions we can't perceive? Imagine this: advanced civilizations might not be hiding in distant galaxies or behind impenetrable barriers of space and time. Instead, they could be thriving in higher dimensional realms, completely invisible to our 3-dimensional tools and senses. Just as we can't see ultraviolet light without the right instruments, we might be missing entire civilizations because we lack the ability to detect or interact with their dimensional reality. This idea isn't as far-fetched as it sounds. If hidden dimensions exist, as many theories suggest, they could provide a framework for life forms that operate in ways we can't even begin to imagine. For instance, a higher dimensional civilization might have access to technologies or forms of communication that are entirely beyond our comprehension. They could be sending signals or interacting with our universe in ways that we simply can't detect with our current methods. Think about how we search for extraterrestrial intelligence today. We look for radio signals, laser pulses, or other forms of communication that fit within our understanding of physics. But what if alien civilizations are using methods that rely on higher dimensional physics? Their signals might be passing right through our detectors, completely unnoticed because we're only equipped to perceive three-dimensional phenomena. This raises an intriguing possibility, the Fermi paradox, which asks why we haven't encountered alien life despite the vastness of the universe, might have a dimensional explanation. It's not that the universe is empty, it's that we're looking in the wrong dimensions. But here's the challenge: even if higher dimensional civilizations exist, how would we ever detect them? Our tools and theories are built for a three-dimensional world, and expanding our search to include hidden dimensions would require a fundamental shift in how we approach the search for extraterrestrial intelligence. It might mean developing entirely new technologies or rethinking the very nature of communication and observation. This idea also invites us to consider what higher dimensional life might look like. Could beings in these realms have evolved senses that allow them to perceive and interact with dimensions we can't even imagine? Would their understanding of time, space, and reality be so different from ours that communication would be nearly impossible? These questions push the boundaries of not just science, but also philosophy and our understanding of life itself. As we continue to explore the mysteries of hidden dimensions, the search for extraterrestrial intelligence takes on a new dimension, literally. It challenges us to think beyond the limits of our perception and consider the possibility that the universe is far more complex and interconnected than we ever imagined. And with that, we move closer to our final theory: how hidden dimensions could shape the future of physics and our understanding of the cosmos. Now, as we reach the final chapter of our exploration, let's turn our attention to how hidden dimensions might redefine the very future of physics. Imagine a world where the boundaries of our understanding are not just pushed but completely rewritten. Hidden dimensions could hold the key to unlocking some of the most profound mysteries of the universe, offering a new lens through which we can view reality itself. One of the most exciting possibilities is that hidden dimensions could provide the missing link between quantum mechanics and general relativity. These two pillars of modern physics have long been at odds, each describing the universe in ways that seem incompatible. But what if hidden dimensions act as a bridge, connecting the quantum world of particles with the vast, curved spacetime of Einstein's theory? This unification could revolutionize our understanding of everything from the smallest particles to the largest structures in the cosmos. Consider this: hidden dimensions might also open the door to entirely new technologies. Just as the discovery of electromagnetism paved the way for everything from radios to smartphones, understanding higher dimensions could lead to breakthroughs we can't yet imagine. Imagine harnessing the power of higher dimensional physics to create energy sources, communication systems, or even modes of transportation that defy our current limitations. The possibilities are as vast as the dimensions themselves, but the impact of hidden dimensions goes beyond just technology. They could fundamentally alter how we perceive the universe. For instance, if we discover that time is a higher dimensional construct, it might change how we think about causality, the flow of history, and even the nature of existence. Could we one day manipulate time itself or travel through dimensions as easily as we move through space? These questions might sound like science fiction, but they could become science fact as our understanding deepens. Of course, exploring hidden dimensions won't be easy. It will require bold new experiments, innovative theories, and perhaps even a complete rethinking of what we consider possible. But the rewards could be extraordinary. By embracing the idea of hidden dimensions, we might not only solve some of the greatest puzzles in physics, but also uncover entirely new realms of knowledge. As we stand on the brink of this new frontier, one thing is clear: the journey into hidden dimensions is just beginning. It's a journey that will challenge our assumptions, expand our horizons, and ultimately reveal a universe far more intricate and interconnected than we ever dreamed. And with that, we conclude our exploration of 30 theories about the universe's hidden dimensions. a journey that has taken us from the smallest strings to the vastness of the multiverse, and now to the limitless possibilities of the future. So, what do you think? Could hidden dimensions hold the answers to the universe's greatest mysteries? Share your thoughts in the comments below, and don't forget to like, subscribe, and hit the notification bell to stay updated on our next cosmic adventure. Until then, keep exploring, keep questioning, and keep imagining the extraordinary. The universe is waiting. As we bring this journey to a close, let's take a moment to reflect on the incredible tapestry of ideas we've explored. From the intricate vibrations of string theory to the mind-bending possibilities of the multiverse, each of these 30 theories offers a unique glimpse into the hidden dimensions that may shape our reality. Together, they paint a picture of a universe far more complex and interconnected than we've ever imagined, a universe where the boundaries of space, time, and existence itself are constantly being redefined. These theories don't just challenge our understanding of the cosmos, they invite us to rethink what's possible. Whether it's the idea of gravity leaking into higher dimensions, the holographic nature of reality, or the potential for parallel universes existing alongside our own, each concept pushes the limits of human curiosity and creativity. They remind us that the universe is not just a place to observe but a puzzle to solve, a mystery to unravel, and a story to tell. But perhaps the most exciting part of this exploration is what lies ahead. Hidden dimensions aren't just a scientific curiosity, they're a gateway to the future. They could hold the answers to questions we haven't even thought to ask yet, from the nature of dark matter to the origins of life itself. And as we continue to probe these mysteries, we're not just expanding our knowledge, we're expanding our sense of wonder. So, what do you think? Could hidden dimensions be the key to unlocking the universe's deepest secrets? Or do you have your own theories about what lies beyond the dimensions we know? Share your thoughts in the comments below. We'd love to hear your ideas and continue this conversation. And if you've enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell so you never miss an adventure into the unknown. Thank you for joining us on this exploration of the universe's hidden dimensions. Until next time, keep looking up, keep asking questions, and keep imagining the extraordinary. The universe is full of surprises, and who knows, the next great discovery might just be waiting for you.